Welcome everybody to Integrated Math 3. In today's episode, we'll be discussing chapter 2.2.3, which is even and odd functions. Let's start off with what an even function's definition is. This is a very definition-based kind of section here. An even function is a function that is symmetric to the y-axis. Right, function that's symmetric to the y-axis. So we know a few even functions, actually, even though we haven't really been introduced to them explicitly in that way. We've seen this one before, y equals x squared. Now this is an even function because if you graph him just as he is, notice how he has symmetry across the y-axis, right? If I was to take a knife and kind of cut him down this way like a cake, you'd be able to fold one piece on top of the next. Totally an even function. Now, before I move on to the next couple of examples, let's take a look at what an even function would not be. An even function would not be this, like y equals x minus 1 squared. That would not be an even function. And the reason why is because even though it's the same parabola, if we remember from transformations, it's being shifted to the right by 1. And one of the consequences of shifting that parabola to the right by 1 is now, even though the parabola is symmetric across its vertex, if I was to take the, like a knife and cut down the y-axis like that, I wouldn't have symmetry across the y-axis. So this one would be considered not even, but this one here would be considered even. All right? So let's just make sure that we're clear about that. I remember that used to confuse me a lot when I was younger about, what an even function was. And so since this guy's not even, let's go ahead and take a look at a couple more examples of even functions here. So we know this one here, like y equals the absolute value of x. He's definitely an even function. We've seen that before. And he looks like this, right? And he's just a v function. Again, if I was to cut him down the middle, there would be no issues. We would know that he is symmetric across the y-axis. And so from here, the way to test whether or not a function is even could be graphically. In fact, I have shown you the way to verify if a function is even via graphical. But of course, we can't always graph every single function that we see to determine if it is even or odd. Case in point, if I was to say, if I was to give you this, if I was to say y equals x to the fourth plus 6x squared plus 7. If I was to ask, is this function even or odd? Well, right now, we have no concept of what this graph even looks like. We've never seen a fourth power function before, and yet there's a possibility I'm going to ask you whether or not this thing is even or odd. And so how would we determine that? Well, let's take a look at one of the final transformations that we're ever going to learn, and that is when you rotate something or flip something about the y-axis. And let's take a look at our x squared right now. So I'm going to go and just pop him out on the side here. In fact, I'm going to make a little bit of space. I'm going to remove my non-even function here, so get rid of him if I can. There you go. And I'm going to introduce to you what this does. F of x versus f of negative x. Now, let's take a look at what this negative on the inside does. What does this transformation do? Well, let's take a look at something that we do know. If I was to do, say, versus negative f of x, well, we know that when we have a negative sitting on the outside of a function, well, what did that do? When the negative was sitting outside the function, what it would do to the graph is it would take the graph and it would shift it upside down. So in the case of negative x squared, right, the parabola would no longer be facing upwards, it would be facing downwards. And what effectively happened was the original parabola that was facing upwards like this, I'll go ahead and just kind of dot him out like that, was rotated and flipped across the x-axis that way. And so now from here, what would make sense about this transformation? Well, if we were to draw it, if we were to draw this thing, here's our standard parabola here. Well, since the transformation is happening before and it's affecting the x, does it make sense, hopefully, that it would be rotated this way across the y-axis? And so what would happen is this parabola would literally be, instead of facing forwards, it'd be facing backwards. We'd be looking, I often like to say, we're looking at his back instead of looking at his front. Now, if you notice, what happens when we have a parabola that's even and we're looking at his back? Well, nothing changed, right? So this is no change. No change from before. And so that is how we determine whether or not a function is even. The idea is that if f of negative x equals f of x, then f of x is an even function. If f of negative x is equal to f of x, then f of x is an even function. Okay? So again, let's talk about what each of these things means. This right here means the function's back, right? The function's back. This right here is the function unchanged. Okay? So let's see how we could do that algebraically. If I was to, we're going to ignore this example for now, but let's say, again, if I did f of x equals x squared, if I was to do f of negative x, well, that would literally be negative x all squared. Well, what happens if I take a negative thing, no matter what it is, and I square it? Well, what I get is I get the positive version of that thing. So same thing with this absolute value example. Let's say I call him g of x. If I say g of x is equal to absolute value of x, which means g of negative x would be the negative, or the absolute value of negative x. And of course, if I was to absolute value anything negative, I would just get the absolute value of itself. And so notice how in both examples here, the notion of sticking a negative inside the function did not change the nature of the function at all. And that's why both of these functions, x squared and x, are both even. So let's try to apply this concept into this harder example here, where we have f of x, or y, is equal to x to the fourth plus 6x squared plus 7. So let's try and determine if this thing is even or odd. So again, what I'm going to do algebraically, because again, I've got no concept of what this graph looks like. What I'm going to do is I'm going to go ahead and plug a negative x into each of my x's. So negative x to the fourth plus 6 times negative x squared plus 7. So let's see what happens. Let's just go and evaluate this thing. Again, anything negative to an even power is going to become positive, right? So x to the fourth. And then again, for the same reason, the negative x all to the fourth becomes positive, the negative x all squared is also going to become positive. Again, we saw that a few seconds ago in this example up here. So plus 6x squared, and then plus 7. So nothing changed, right? There was no change in the function when I put down a negative x in there. So therefore, we can say f of x is even. Hopefully that makes sense. Let me give you an example of when it doesn't go the way we want it to go. So let's say I give you f of x is equal to x to the fifth minus 7x to the fourth plus 2. So now again, let's see, are we going to determine whether or not this thing is even or odd? Actually, we don't know what an odd function is, so we're just going to determine if this thing is even. So it's either going to be even or neither at this point. So if I plug in a negative x, again, why am I plugging in a negative x? Because I don't know what this graph looks like. And in fact, in a couple seconds, I'm going to go back and I'm going to graph this thing on Desmos and show you that it doesn't change if you rotate it. And so if I plug in a negative x to the fifth minus 7 negative x to the fourth plus 2. So any negative thing, negative thing raised to the fifth power is going to be a negative version of that thing, because the odd power will allow the negative to survive. And so this negative here will be 7, so it'll be negative 7. And then again, the negative to the fourth will just become x to the fourth, and then plus 2. And you see how the function fundamentally changed, right? Like there's nothing, like there's something different about it. It's not what it was before. This is neither. And again, we're saying neither because eventually we're going to roll into the odd function. And so this is neither even nor odd, but for now, you don't need to worry about an odd function for now. Okay, let's cycle back to this guy here real quick. I'm going to go to Desmos real quick, x to the fourth plus 6x squared plus 7. So x to the fourth plus 6x squared, x squared, and then plus 7. Okay, so let's scroll back. Let's scroll out here a little bit. Okay, cool. So notice how he's very parabola-like, you know. And so imagine if I was to throw down negatives in there, nothing would change. So let's go and just surround our x's with parentheses, and then watch what happens if I plug in a negative right here, and if I plug in a negative right here. Nothing changed, right? In fact, I'll go ahead and put down the other function without the negatives. So x to the fourth, I'll actually just go and copy him. I'll copy him down. So I'll remove the negatives. Notice how the blue and the red overlap each other. So again, just to reiterate, to find this thing algebraically is to see this thing graphically not changing at all. Hopefully the graphical visual of that reemphasizes that point. So again, the idea of a function being even boils down to this idea right here. If you look at the function's back and it becomes the function unchanged, you are dealing with an even function. Okay, let me clean up the board real quick. I'll be right back with the odd function. And we are back now with the definition of an odd function. And an odd function is defined as a function that is symmetric to the origin or has rotational symmetry. And so in order to illustrate this, I'm going to first start off by drawing an example of an odd function. And so if I was to do y equals x to the third power, if I was to draw this thing, it looks like this. Now, it's kind of hard to show, but if I was to take this bottom left side here and flip it upwards into this quadrant, I'm hoping you would see that the next iteration would look like this. Right? Again, what did I do? I just took the bottom side and I just flipped it off. So this thing should be gone, flipped it upwards into the second quadrant, and now this piece that's in the second quadrant here, I'm going to take it on the next move and move him over here. And what will happen is this piece will then go away and then overlap with this image right here. And so hopefully that makes enough sense. But if not, the rotational symmetry might make a little more sense. If I go to my trusty paint program here, if you look at the exact same function here, I'm going to rotate it 180 or 90 degrees first, and then I'll rotate it 90 degrees again for a total of 180 degrees. Notice what happens. I end up with the exact same image, but if you notice these numbers on the axis, they're on both axes, they're both upside down, right? And so that's because this thing does have rotational symmetry, and meaning it's the same whether you look at it right side up or upside down. So again, graphically, that is why a function would be defined as odd. Let's take a look at a couple other examples of some odd functions here. So we know another one. Another example of an odd function would be something you learned in Integrated 1, y equals x. So if you, and I'll let you guys do this yourselves, but if you look at him, if you were to flip this image 180 degrees, you would get itself. And so the last one is something that you have recently learned. It's y equals 1 over x. And so again, if you want, feel free to go ahead and take this image and rotate him upside down and see what happens. You will end up getting the exact same image. So of course, like the even function, we can't always graph everything. I mean, what if I gave you something that looked like this? If I said f of x f of x is equal to, let's say, x to the fifth minus 7x cubed plus 2x. How would we be able to figure out if that thing was even or odd without graphing it? Well, from here, like the way the even function had a way of plugging in the back version of the function, the odd function operates the same way. And so from here, let's go ahead and define what that is. Let's see, if, I'll move him down, if f of negative x, again, the function's back, right, is equal to negative f of x, meaning the upside down version of the function, then f of x is odd. So again, let's go ahead and define what those are, because that way we can get those into words here. So again, this is the function's back, right? So this is the function's back. This is the function upside down. Okay, so if by looking at its back, you're looking at it upside down, then you're going to be odd. Now, again, let's take a look at this in Desmos real quick, just to make sure that we are where we want to be. So I'll go ahead and get rid of these guys here from the last example. If I did x cubed in here, he would look like that, right? And so now if I was to do negative x cubed, notice how he's upside down now, right? Instead of going from the bottom left to the top right, the negative version is now going from the top left to the bottom right. Now again, I'll go ahead and do negative x and then quantity cubed. Notice how the green and the blue overlap each other now, right? And so by putting a negative on the inside, by looking at his back, it is graphically the same visual effect as if I was to look at him upside down. And so that's how we're going to determine if a function is even or odd without having to graph that function. So if I look at f of x, let's go and check them out. I'm going to do f of negative x. Again, I'm referring to this function up here, the one that I just wrote in right there. That's going to be negative x to the fifth minus 7 times negative x cubed plus 2 times negative x. Well, luckily, all the exponents here are odd, which means the negatives will actually survive the algebraic manipulation. I'm going to have negative x to the fifth. Negative is going to become positive 7x to the third, and then minus 2x. Now, again, you may be thinking, based on our neither version of the example, you're like, wait a second, the function completely changed. There's no way this thing is odd. Well, let's see what happens if we factor out a negative from this expression here. If I factor out a negative, that x to the fifth will go positive, the 7 will become negative, and then the 2 will become positive yet again. So what I have is I have the original version of the function, but negativized. And so because I have the upside down version of the function, I can then say that f of x is odd based on that analysis. So again, let's see what happens if we end up with a neither version of this. So if I do actually, let's change up the letters here just to make sure that we are comfortable with all kinds of function notation. Let's say g of x is equal to x to the fifth plus 2x squared. So again, is the function even, odd, or in this case, neither, right? Because it could be neither. So g of negative x, again, no concept of what this graph looks like, right? I'm not going to bother making a table out of this thing. I'm going to say negative x to the fifth plus 2 times negative x squared. Well, it looks like this will become negative x to the fifth, but then the 2 will stay positive because this negative x all squared will become just regular x squared. And notice how if I factor out a negative like I did in the last example, the function fundamentally changes, right? Like there's nothing I can't get back to this original version, and it's not like this version is the negative version of its original self. So that's why this g of x would be neither. So hopefully that makes sense. Hopefully that clarifies even and odd functions for all of you. As always, please leave comments or questions in the comments area, and that'll wrap it up for even and odd functions. I will see you all in the next episode.